Good evening. Am I audible?
Yes, sir.
Okay. So any doubt from last class to any one of you?
No, sir.
Let me define you another term related to this heat conduction. Kirchhoff's law of electricity, or simply Kirchhoff's current law. Which is based on conservation of charge Charge is nothing but particle. So let me define you. Suppose you have a road like this. If 4 individuals, or let's say 3 individuals coming along this way, 2 individuals coming along this way, if one is going along this way and someone asks you how much individual will go along this way if there is no accumulation of individual at this particular junction. In this part, I've just asked, if you have 3 individuals along this way, 2 individuals along this way, and one is going along this path, so how much individual will go along this direction if there is no accumulation of individual at this particular junction? Asma? Samaira? What will be answer? Just count how many individuals are going towards the junction. So one is this and the other is this. So in total, you have 5 individuals going towards the junction. Is it clear? Now just count how many individuals are going out of the junction. So we have just 1. So we're left with how much part? 4. So that sum of all outgoing must equals to sum of all incoming at this particular junction, since there is no accumulation of individual at this particular junction. Is it clear?
Yes, sir.
Nara, any doubt?
No, sir.
Similarly, on the basis of Kirchhoff's electricity or Kirchhoff's law of electricity for current law, which is based on flow of charge or flow of electron state, if we have junction like this, in which I1 will be going along this direction, I2 will be along this direction, I3 along this direction, and I4 along this direction. So if there is no accumulation of charge at this junction, so sum of all current at the junction must equals to 0, or total incoming current must equals to total outgoing current. Is it clear?
Yes, sir.
So if there is no accumulation charge at junction, then total inward current must equal total outward current sum of all current going towards the junction must be equal to sum of all current going out of the junction. Or if you add them together, sum of all current at this particular junction must equal to 0. Sakshi, is it clear? Okay, just write it down.
Done, sir.
Asma, you have written?
Done, sir.
Now, let me give you a question related to this concept. Suppose you have rod this particular rod is at 0 degrees Celsius. This rod is at 30 degrees Celsius. And this rod is at 90 degrees Celsius. We have in this arrangement 3 identical rod arranged as shown. Find temperature of junction. So how to calculate temperature of junction? Now in this particular arrangement, we don't have any information about direction of current, in which direction it is flowing. So just take this particular junction having temperature X and take each direction of current to be going outward of this particular junction. Just suppose initially. So in this direction, H1 going outward, and this conductor H2 going outward, and this conductor H3 going outward. So if you calculate the value of H1, H2, H3, H1 is Ka divided by L times temperature difference X minus 0, according to the above formula of heat transfer. Similarly, we can write for H2, Ka divided by length, temperature difference X minus 90, and H3 equals to Ka divided by L, X minus 30. So we have 3 different current H1, H2, H3 flowing in this particular arrangement. Now, according to Kirchhoff's current law, sum of all current at the junction must equal to 0. Since all are going outward, take it as positive. So sum of these H1, H2, H3 must equal to 0. So sum of all heat current at junction, according to Kirchhoff's current law, must equal to 0. Put the value of each term, Ka by L times x minus 0 Ka by L x minus 90 plus Ka by L x minus 30 equals to 0. Now simplify this expression and try to find x. Try to solve. Take out Ka by L as common, move it to other side, and you're left with x and constant part. Just take out K by L as common. So you're left with x minus 0, x minus 90, x minus 30 equals to 0. These term, coefficient of this particular part, on moving to right side becomes 0. So you're left with x plus x plus x, 3x, 90, 30, 120 equals to 0. So x equals to 120 divided by 3, that will be 40 degrees Celsius. Samira, is it clear?
Yes, sir.
Nahara, any doubt?
No, sir.
Now put this value of x in the above equation for h1, h2, h3. So in first part, x is 40. So you'll get 40 Ka divided by L. In second part, if you put the value of x to be 40, 40 minus 90 will be minus 50 Ka by L. In third part, x is 40 minus 30, so it will be just 10 Ka by L. Now just add these three different equations, you will get 0. So in this part, H1 is in positive. So you'll say your assumed direction is same. So it must be flowing along this direction. H2 is in negative. So change the direction of what you have assumed. So H2 would be along this direction. And H3 is in positive. So it must be along its own direction, what we have assumed. Now just compare. H2 is incoming current to this junction, and H1 and H3 is outgoing current from this particular junction. So you will say sum of all incoming current must equals to sum of all outgoing current, or sum of all current at the junction must equals to 0. Is it clear?
Yes, sir.
Samara, any doubt?
No, sir.
Okay, just write it down.
Done, sir.
Done, sir.
Nara, you have written?
Yes, sir.
Asma, done? Sakshi? Okay. Now, on the basis of flow of heat current, we have to calculate combination of rod for series combination as well as parallel combination. So next is combination of rod. First is series combination. Suppose you have a rod which is at temperature T1, thermal conductivity K1, and of length L1. Another rod of same area of cross section but of different length connected to temperature T2, thermal conductivity K2, and length L2. Let's say temperature of this particular junction to be T0. Now, on combining this particular rod, combination will be like this. One end is at temperature T1, other end is at temperature T2. Combine equivalent K, total length L1 and plus L2, and area of cross section of this is A, and this is also A. So we have to compare these two arrangements to find K equivalent in terms of K1 and K2. So let me define you how to solve. First, heat current in rod 1. According to the formula, H equals to Ka divided by length temperature difference T1 minus T2. T1 is this and T0 is temperature of this particular junction, which is at end point of this rod L1. So from this part, first calculate T1 minus T0. So it will be HL divided by K into A. Let's say this is equation first. Similarly, for second rod, heat current in rod 2. H equals to K A divided by length, temperature difference T0 minus T2. I've just assumed in this particular arrangement, T1 is at higher temperature, and T2 is at lower temperature. So current must be flowing from higher temperature to lower temperature. So H1 will be along this direction and H2 will be along this direction. So if you calculate temperature difference for this second part, T0 minus T2 equals to H into L divided by K into A. Let's say this is equation 2. Aisha, is it clear?
Yes, sir.
Okay, just write it down to this part.
Done, sir.
Done, sir.
Asma, done? Nahara, written?
Yes, sir.
Now, if you add these two equations, on adding equation first and second, you will get T1 minus T0 for first part, T0 minus T2 for second part, which is equals to H1 L1 by K into A plus H2 L2 by K into A. T0 and T0 will get cancelled out. So you're left with T1 minus T2 equals to H1 L1 by K1 into A plus H2 into L2 by K2 into A. Let's say this is equation third. Now we have to calculate for equivalent part. For equivalent rod, H equivalent equals to K equivalent, area of cross section is A, and total length on combination will become L1 plus L2. Temperature difference is T1 minus T2. So if you calculate temperature difference So T1 minus T2 equals to H equivalent L1 plus L2 divided by K equivalent times area. Let's say this is equation 4. Now we have same term in equation 3 and equation 4. And as we know, in series combination, current will be same in each rod. As in series, H1, H2, and H equivalent becomes equal to H. So from equation 3 and 4, we may write H equivalent times L1 plus L2 divided by K equivalent times A must equals to H times L divided by K1 into A, H times L divided by K2 into A. H by A, H by A, H by A will cancel out from both sides. So you're left with L1 plus L2 divided by K equivalent equals to L1 by K1, L2 by K2. So this will be our final formula for series combination of rod. Samaira, any doubt?
No, sir.
Sakshi, is it clear? Okay, just write it down.
Done, sir.
Done, sir.
Nara, done?
Yes, sir.
Okay, let me give you a question related to this combination. Find K equivalent for the combination. Just use the above formula. We have L1, L2, K1, K2. Simplify it. You got any answer? Any one of you?
No, sir.
Nahara, any problem while solving?
No, sir, I'm doing.
Okay. Let me solve. So Myra, just check your calculation. Just see, we have L1 0.4, L2 0.1 divided by K equivalent, which we have to calculate. L1 is 0.4, K1 is 0.8, L2 is 0.1, K2 is 0.6. So this part and this part will cancel out. This part and this part will cancel out. So 4 in 2 time equals to 8. So 0.4 plus 0.1 becomes 0.5 divided by K equivalent. Take LCM to be 6. So you'll get 3 plus 1, 4 divided by 6. Now on cross multiplication, 0.5 into 6 equals to 4 times K equivalent. So K equivalent becomes 0.5 into 6, 3 divided by 4. So it will be 0.75 watt per meter per Kelvin. Samira, is it clear?
Yes, sir.
Asma Riaz, any doubt? Sakshi?
Sir, can you hear me?
Yes.
Sir, by mistake, I was messaging all my answers to physics MEC, I think.
Okay.
So, yeah, just that.
Okay, you all have done? Nara? Okay, next is parallel combination. You must have learned about this parallel combination. Suppose you have a resistor, this, another resistor, this, whose end are connected to single point, this. So if a current I is going along this, at this junction, it may get divided into two parts since we have two different direction of flowing. So in this direction, let's say I1 is going, and in this direction, let's say I2 is going. So this parallel combination, or in this parallel combination, total individual current flowing across each arm must equals to total current I. Using this concept, we have to calculate K equivalent for this parallel combination. Let's say you have a rod thermal conductivity K1, another rod thermal conductivity K2, both having same length and connected to same temperature. Temperature of this end is T1 and temperature of this end is T2. So for equivalent part, T1, T2, area of this rod, let's say A1, area of this rod, let's say A2. So total area from this point to this point will become A1 plus A2. Length remains same L, and K equivalent. So we have to relate these two terms to find K equivalent. Let's say H1 flowing across it, H2 flowing across it, and total current H equivalent across it. So in this parallel combination, we can say H equivalent equals to H1 plus H2 according to the above relation. So first, heat current through rod 1. So H1 equals to Ka divided by L, temperature difference T1 minus T2. Similarly, heat current through rod 2, H2 equals to Ka divided by L, temperature difference T1 minus T2. And last, for equivalent part, H equivalent equals to K equivalent times A1, A2 divided by L times temperature difference T1 minus T2. Now, according to the above relation, we may write, first write it down to this part.
Done, sir.
You all have written? Nahara? If you have to calculate K equivalent, so according to the above concept, we can write for parallel combination, total current must equals to sum of all individual current. So put the value of each part, K equivalent times A1 plus A2, divide by length L, temperature difference T1 minus T2, H1 K A divide by length, temperature difference T1 minus T2, plus H2 K A by length L, temperature difference T1 minus T2. So we have T1, T2 in all these three terms. So they will cancel out. L will cancel out. So we're left with K equivalent times A1 plus A2 equals to K1 A1 plus K2 A2, or move this A1 A2 to right side. So K equivalent would become K1 A1 plus K2 A2 divide by A1 plus A2. So this will be our final result for this combination of parallel. Aisha, is it clear?
Yes, sir.
Done, sir.
Sakshi, you have written? Okay. Asma, done? So this is all about heat transfer by conduction method. Next, let me define radiation. Samara, what do you mean by radiation? Any idea? Okay, let me define you. First, what do you mean by wave? Suppose I have taken a stone and just throw it. So thrown will themselves will move from one point to another point by taking that much amount of energy or momentum, or you'll say it themselves move to transfer energy and momentum from one point to another. But suppose you have wire or a string like this, on which by hitting any particular hard obstacle to it, there will be disturbance created like this. So this disturbance will propagate along this medium, but the particle which is initially at this point will tend to be at their own position. They will only vibrate up and down to create this disturbance, which propagates along this entire string from one point to another and carrying energy and momentum without the displacement of matter particle. This phenomena is called wave. So wave is nothing but a phenomena of transfer of energy and momentum from one point to another without the displacement of matter particle. So it is phenomena of transfer of energy and momentum from one point to another without displacement of matter particle. Samira, is it clear?
Yes, sir.
So this wave may be of three different types. First is mechanical. You must have learned about it in your earlier class about sound, a wave which require any medium for their propagation. Medium is required. Second, matter wave. You must have learned about it in your chemistry about de Broglie hypothesis, which defined even matter particle, electron, proton, alpha particle, themselves behave as wave, which is defined by de Broglie wavelength. So the wave associated with those particles, electron, proton, so on, termed as matter wave. And last, electromagnetic wave, a wave which does not require any medium for their propagation, and they can even travel through vacuum. So no need of medium. Any doubt related to these three different types of wave? Aisha?
No, sir.
So in this electromagnetic wave, we mainly have 8 different types of wave. First is cosmic rays. Second one is gamma rays, X-rays, ultraviolet rays, visible light, infrared rays, microwave, and radio wave. You have to learn about this electromagnetic wave in more detail in your next class, that is in class 12. In this chapter or in this part, we have to define only for these two waves. Visible light, to which our eye is sensitive to, and next is IR rays, which is also called heat wave. Okay, first write it down to this part.
Done, sir.
Done, sir.
Nahara, you have written?
Yes, sir.
Asma, done? So from this, we may define what do you mean by radiation. So you say radiation is nothing but electromagnetic wave, which does not require any medium for their propagation, and they can travel even through vacuum at the speed of light. So radiation is which now related to this radiation, let me define you concept, which is called reversed theory. If someone asks you why we feel cold in front of ice, and similarly, why we feel hot in front of fire. So how will you define according to this or according to physics? Let me define you. According to Provost's hypothesis, it states every object which having temperature greater than 0 Kelvin, so it will have thermal kinetic energy. So it will radiate as well as absorb radiation at all time. So all object having temperature greater than 0 Kelvin will absorb and emit radiation at all time. Now, on the basis of their body temperature, they may radiate cold radiation or hot radiation, which may define on the basis of their relative parameter or their relative measurement. Now, on the basis of this theory, let me define you why we feel cold in front of ice, and similarly, why we feel hot in front of fire. Suppose there is an individual standing in front of ice. So in first part, human body having temperature, normal human body temperature 37 degrees Celsius. So in terms of Kelvin, it will be 310 Kelvin. This ice cube, which is initially at 0 degrees Celsius, so in terms of Kelvin, it will be 273 Kelvin. So the more the temperature of a body, it will radiate more amount of radiation. So ice having lower temperature, so it will radiate less amount of energy. Human body having more temperature, so it will radiate more amount of radiation like this. Since more amount of radiation is going out from this human body, so net flow of radiation will be from this point to this point. Due to this net flow of radiation, which is going out of body of this human body, temperature of human will tend to decrease. Hence, he must feel cold due to flow of radiation out of their body. Similarly, in second part, temperature of human 37 degrees Celsius. Let's say temperature of fire to be 100 degrees Celsius. So in terms of Kelvin, it will be 310 Kelvin and it will be 373 Kelvin. Since temperature of fire is greater as compared to human body, so it will radiate more amount of radiation along this side, and it will radiate less amount of radiation along this side. So net flow of radiation in this case will be from this point to this point, which will tend to increase the temperature of body, hence we feel hot in front of fire. Is it clear? These two different terms?
Yes, sir.
Samira, any doubt?
No, sir.
Okay, just write it down.
Done, sir.
Okay, you all have done? Nahara?
Yes, sir.
Okay. Next is black body radiation. So to define black body radiation, let me define you some term related to that part. First is, suppose you have metallic object like this, which is placed over a burner. So radiation will fall or heat will fall on this particular surface. Let's say Qi. So some radiation may get reflected like this. So this will be Q reflected. Some radiation may get absorbed and some radiation may get transmitted along this way. For this incident radiation Qi, we may have these different terms: Q reflected, Q absorbed, and Q transmitted. So on the basis of these three terms, we may define first absorptance, which is also called absorptive power or absorptivity. So absorptive power or absorptivity is nothing but the ratio of total radiation absorbed by this object to the total radiation falling on it. So this is the ratio of total radiation absorbed to the total radiation falling on it. So A equals to Q absorbed divided by Q incident. Since Q is nothing but heat having unit joule, so Q absorbed divided by Q incident both will have same unit. So you'll get absorptive power to be unitless quantity. Next, reflectance or reflectivity or reflective power denoted by R. So it will be total amount of radiation reflected by that object to the total radiation falling on it. So it will be the ratio of total radiation reflected by body to the total radiation falling on it. So R equals to Q reflected by Q incident. Again, Q reflected and Q incident will have same unit. So the ratio of these two same quantity will give you unitless term. And third, on the basis of transmittance or transmitting tendency. Next is transmittance, transmittivity or transmittive power, denoted by T. The ratio of total radiation transmitted by body to the total radiation falling on it. So T equals to Q transmitted divided by Q incident. So again, it will be unitless quantity. Samara, any doubt?
No, sir.
Okay. Sakshi, is it clear? Okay, just write it down.
Done, sir.
Answer.
Nahara, written.
Yes, sir.
Asma, now let me define you the relation between these three terms. So we may write on the basis of conservation of energy using conservation of energy. Amount of radiation absorbed amount of radiation reflected and amount of radiation transmitted must be equals to total amount of radiation falling on it. So if we divide this entire term by Qi, you will get Q absorbed divided by Q incident, Q reflected divided by Q incident, and Q transmitted divided by Q incident equals to Q incident divided by Q incident. This particular ratio, this term, QA divided by QI will be absorptive power A, QR divided by QI, reflectivity R, and Q2 divided by QI is transmittance T, which must equals to 1. So this is first relation related to these three terms. Now, first, for vacuum, there is no ability of vacuum to absorb any radiation, to reflect any radiation. So you will say T will be equals to 1. So we can say vacuum behaves as perfect transmitter. Next, for mirror. Since mirror is attached with any non-radiating support from its backside, so transmittance in case of mirror will be 0. So we're left with A plus R equals to 1. Now in this expression, for mirror, it having tendency to reflect more amount of radiation as compared to how much it get absorbed. So it will have tendency to radiate or reflect more and lesser tendency to absorb radiation, or you can say less absorbing tendency and more reflecting tendency. So from this we can conclude good reflector are bad absorber and vice versa. So from this expression, if R will be more, A will be less, so that the sum of these two terms, A plus R, will always equals to 1. So if R is more, it will be good reflector, so A will be less, so it will be bad absorber, and vice versa. Samira, is it clear?
Yes, sir.
And last, in case of black body, reflectance will be 0, no transmitting tendency, so A will be maximum, that is A, 1. So black body behaves as perfect absorber. You may define black body as a body which having tendency to absorb all radiation falling on it. A body having tendency to absorb all radiation falling on it. Now just write it down to this part.
Done, sir.
Sakshi, any doubt related to this part? Nara, you have written?
Yes, sir.
Okay. Now let me define you property related to this black body or black body radiation. So to define black body radiation, let me explain you two more terms. First is emissive power. Samara, do you know about what do you mean by intensity? Intensity is amount of energy radiated by any object, let's say bulb, at what rate it is radiating energy per unit its area, per unit time is called its intensity. Similarly, emissive power defines intensity of emission of any object. So emissive power is the amount of radiation emitted by hot body per unit area per unit time. So energy emitted divided by area of object multiplied by time. This is also called intensity of emission. So its SI unit related to this part will be energy, joule, area, meter square, times second. So joule per second, meter square, or joule per second is also called watt, watt per meter square. This is first term. Next is, if you have to compare intensity of emission by any ordinary object to the intensity of emission of any black body at given temperature. So this ratio is called emissivity. Denoted by epsilon or small e. So this is the ratio of emissive power of ordinary body to the emissive power of black body at given temperature. So epsilon equals to emissive power of any ordinary object divided by emissive power of black body. So it will be unitless quantity since it is a ratio of same term for two different objects. So it will be unitless quantity. It ranges between 0 to 1 and epsilon equals to 1 only for black body. Samira, any doubt?
No, sir.
Asma, is it clear? Okay, write it down.
Done, sir.
Asma, you have done to this part? Okay. Now, related to these terms, let me define you Kirchhoff's law of radiation. It states emissive power of any ordinary object divided by absorptive power that ordinary object is always equals to emissive power of black body at that temperature. You may rearrange this expression like emissive power of any ordinary object equals to emissive power of black body multiplied by absorptive power of ordinary object. I've just moved this denominator to right side. Now in this expression, this quantity will be constant for a particular temperature. So you'll say this term will be proportional to this term. It means good absorber are good emitter. So you'll have to state or prove this particular statement by a body having good absorptivity will have good emitting tendency. So you may define this Kirchhoff's law of radiation. So let me prove this statement. So from this, we may conclude good absorber are good emitter. And since it having good absorbing tendency, so it will have less reflecting tendency. So it will have bad reflector. Good absorber are good emitter, but bad reflector. So for this statement of Kirchhoff's law, you will say at same temperature, the ratio of emissive power and absorptive power of any ordinary object is always equals to emissive power of black body at that temperature. Okay, first write it down, then I'll prove this statement. Aisha, any doubt?
No, sir. Done, sir.
Nahara, written?
Yes, sir.
Okay. Now, related to this concept, you'll be asked, suppose you have different color of dye in a particular pan. Let's say one is black, next is blue, and next is red. Black, blue, and red, which is exposed to sun. And now kept in any dark room. So which of these three dyes will supposed to glow more? Red, blue, black. Samira, any guess? First, tell me which of these dye will having tendency to absorb more amount of radiation? The red one, blue one, or black one?
Black one.
Good. So just use the above expression of Kirchhoff's law. Good absorbing tendency will have good emission as well. So which will glow more? Since black object having tendency to absorb more radiation. So according to Kirchhoff's law, you will say emissive power is directly proportional to absorptive power. So good absorbing tendency will have good emission tendency as well. Is it clear? So which of these three dye will glow more in dark room? Samira?
Black one.
Good. So black body having tendency to absorb more radiation, so it must have tendency to emit more radiation. So in dark, it will radiate more, so it will glow more. Asma, any doubt? Okay. You all have done till this part?
Yes, sir.
Yes, sir.
Okay. So let's stop here for today. In next class, I will prove this statement. Then I will define you application of this Kirchhoff's law, that is Stephen's law and Newton's law of cooling. Then we'll start thermodynamics, new chapter. Okay.
Okay, sir.
Okay, then we'll continue next class.
Thank you, sir.
Thank you, sir. Bye,
Thank you.
sir.